Well, today we've really only got one new topic. It's called momentum. That's what we're looking at today. There's another secondary topic that goes sort of along with this called impulse, but impulse is really just a rearrangement, just another look at something that we already know, Newton's second law of motion. We're going to spend most of our time today on linear momentum involving straight line motion, and then we're going to look at the end at rotary motion, because the spinning type of motion also has momentum involved with it. So here's what linear momentum is defined as. It's the product of an object's mass and its velocity. The Greek letter rho is usually used to describe momentum, and sometimes the English letter p, and it's the product of m times v. It's a vector quantity because velocity is a vector quantity, and you're multiplying a mass times a vector quantity. So the magnitude of momentum is just equal to the product of speed times mass, and the direction of this vector is just the same as the direction of the velocity involved here. Well, we find that there's a law here in effect called the law of conservation of momentum, and what it's saying is, as long as there's no net force external to the system that's acting on an object or an entire system, the total momentum of the object remains constant. So initial momentum equals final momentum as long as there's no net external force. We could also say, because of the definition of momentum, that initial mass times the initial velocity would then have to be equal to the final mass times the final velocity for that object. Really, this is just a restatement of Newton's first law of motion for a single object, but when we apply this to systems of more than one object, well, then it becomes a powerful problem solving. Let's consider a system that's made of two objects. Object number 1, object number 2. This has a mass we'll call m1. This has a mass we'll call m2. This one's moving with an initial velocity we'll call vi1. This one's moving with an initial velocity we'll call vi2. Now, after some event occurs, a collision or something like that, the total amount of momentum before and after must be the same. So we could say that the momentum initial for object 1 plus the initial momentum for object 2 have to be equal to the initial or the final momentum for object 1 plus the final momentum for object 2. Or, using the terms that define momentum, we could say initial mass of object 1 times the initial velocity for object 1 plus the initial mass for object 2 times the initial velocity for object 2 would have to be equal to the final mass for object 1 times the final velocity for object 1 plus the final mass for object 2 plus the final velocity for object 2. Now, most of the time we don't see changes in mass, but it can happen depending on the kinds of interactions that occur. We could generalize this to more than two objects, as many objects as you like, in fact, and we can use this Greek letter sigma that signifies the sum of. You've probably seen that before. That Greek letter sigma means the sum of what comes afterwards. So the sum of all the initial momenta has to be equal to the sum of all final momenta, or the sum of initial masses times velocities is the sum of all final masses times velocities. Let's look at some applications. One possible way that a number of objects, let's take a couple of objects for a simple case, could interact with each other is in what we call a perfectly inelastic collision. An inelastic collision means the objects stick together, so there's no bouncing back. One object hits the other object, and after this collision, here's the before and after, before, after. After the collision, it's just one stuck together mass. That's an inelastic collision. Here's an example of a problem involving an inelastic collision. Got a 1,200 kilogram car, 12 meters per second speed, collides with a 1,500 kilogram car, moving 5 meters per second, and it's in the same direction as the other car. We're going to assume that they stick together, so that means inelastic collision. What's the final velocity of the two cars, which is now a set of two collided cars, after the collision? Well, let's set this problem up with a before and an after, keeping in mind that before and after should show the same total momentum. I'm going to draw a picture here of a car. My cars are turning into blobs because I have less and less ability to draw a car as the time goes on. So car 1, car 2. Here are the facts. The mass of this car is 1,200 kilograms. Its velocity is originally 12 meters per second. The mass of this car is 1,500 kilograms, and it originally has a velocity in the same direction of 5 meters per second. Now, afterwards, they're stuck together. It says this is an inelastic collision, so 1, 2 coupled together, it's now one single mass. And this thing is going to have a velocity we'll call VF, and it's our objective to find out what that is. Well, the law of conservation of momentum tells me that the sum of the initial momenta is equal to the sum of the final momenta. And momenta are just m times v. So initially, we have two momenta to sum together. Well, momenta are just m times v. So for the first car, we're going to have m1 times v1. For the second car, we're going to have m2 times v2. These are the initial velocities. And then that's going to have to be equal to, well, there's only one object afterwards. It's the m1 plus m2 composite car. And that's times the final velocity. So if we take this equation and simplify it, solve it for what we're looking for, we could say that m1 v1 plus m2 v2 divided by the sum of the two masses m1 and m2, that's going to be equal to final velocity. So now let's just plug numbers in here. The first mass was 1,200 kilograms. The first velocity was 12 meters per second. The second mass was 1,500 kilograms. And the second velocity was 5 meters per second positive, because they're both in the same direction. We're going to divide that by the sum of 1,200 kilograms and 1,500 kilograms, because that's m1 plus m2. Do the calculation. Here's what you find out. That final velocity is 8.11 meters per second. Sort of makes sense because it's somewhere in between the two velocities. Another application that involves momentum is something that we call a perfectly elastic collision. In a perfectly elastic collision, instead of sticking together, in fact, the two objects rebound completely and there's no momentum lost at all. So this object and this object collide with one another. So they're moving toward one another initially. There's a collision. Afterwards, they're moving away from each other, but nothing has slowed down. No mass is lost. The total amount of momentum is still the same. Perfectly elastic collisions don't exist in real life, and so they're a little bit fanciful, but they're something that can be used to model many real-life situations. Solving problems with perfectly elastic collisions is a little more complicated, and so we're going to leave that alone for right now. Another application is rockets and explosions or rifles or things like that. In this case, the net momentum, it's important to keep in mind, before and after the event is constant. But sometimes the initial momentum can be zero. Here's an example. A 45-gram bullet leaves a 2.89 kilogram rifle at 350 meters per second. And the question is, what's the recoil velocity of the rifle? Well, here's what they're getting at with this idea of recoil velocity. If you ever shot a rifle, you know that the thing kicks back, it pushes back, and that's because initially this rifle, which contains the bullet to start with, has a momentum of zero, because even though it's got some mass, the mass is equal to mass bullet plus mass of rifle. When you try to find momentum, initial momentum, well, that's going to be multiplied by initial velocity, and that's just zero. It's not moving at all. That's the before. Here's the after. After the rifle has fired the bullet, now I've got this rifle, which has the mass of the rifle, mr, and it's going to be moving backwards with some velocity that I'll call velocity rifle, vr. The bullet, on the other hand, is going to be moving in the other direction with some velocity I'm going to call vb for bullet, and it's going to have its own independent mass now. It's not part of the rifle. Well, no matter what the situation, we know that momentum has to be conserved. And so we can say that the sum of the initial momenta equals the sum of the final momenta. Well, the initial momentum, it's just zero in this case. So that means zero equals the sum of the momenta of the rifle and the bullet. The momentum of the rifle is mr times vr, And the momentum of the bullet is m bullet times v bullet. So what that means is mr times vr has to be equal to negative m bullet times v bullet. What we're trying to find here is the recoil velocity of the rifle, which is Vr. So we'll solve this equation for that. Vr is just going to be negative mass of bullet times velocity of bullet divided by the mass of the rifle. Well, now we'll plug our numbers in here. First of all, this is negative, and this is 0.0450 kilograms. That's the mass of the bullet, 45 grams in kilograms. And the velocity of the bullet, it tells us, is 350.0 meters per second. That's going to be divided by the mass of the rifle, which is 2.89 kilograms. Well, what's going to happen unit-wise is the kilograms are going to drop out, and that's going to leave us with just the velocity. And so the velocity of the rifle that we calculate turns out to be negative 5.45 meters per second. Now here's what the negative sign means. It just means it's going in the opposite direction as the bullet, because we define the bullet's velocity as positive up here. The number makes sense. The rifle's a lot heavier than the bullet, so you'd think its velocity should be a lot less than that of the bullet.